All right, we are going to wrap up this section 4.7, I think it is, on optimization with just one more, actually pretty short, I think, optimization problem. Just a little different, though, than the other ones we've done, and so you may come across something similar to this in your homework. So it says, find the largest area of an isosceles triangle with base vertices on the parabola, y equals 16 minus 4x squared, and above the x-axis. And the third vertex is at the origin. So let's get a sketch. So let's start by coming up with a sketch of what we have going on here. All right, so let's just draw in, if we can, a not so good looking parabola. And of course, if it's the parabola, so this is my parabola 16 minus x squared. And so that means, of course, that we're up here at 16 on the y-axis. If you were to set 16 minus x squared equal to 0, you are going to cross on the x-axis at 4 and negative 4. And so what are we trying to find here? Here's what we're trying to find. We're trying to find if I have the two vertices parallel and above the x-axis, and then the third vertex is at the origin. So there two are on the parabola and they're above. And this is an isosceles triangle. So when it's isosceles, you have two sides that are equal. And so there's the base vertices, and then there's the third vertex. All right, so the question is where should we have these base vertices? So where should I place those in order to have the triangle with the largest area possible? Right, so these are kind of just different pictures of the same criteria being satisfied, but we're trying to figure out where that point should be to maximize the area. So let's start with that. So we are trying to maximize our area. So it's always where we start, what we're trying to optimize. So maximum area. Now we are trying to find the area, maximum area of a triangle. And so the formula for area of a triangle, of course, is just 1/2 the base times the height. Now we have to be a little careful though here because we're on the coordinate plane. The x and the y already have pre-designated meaning. So now we have to incorporate that into what it's going to mean for the base and the height of a triangle here. So if I'm thinking about, so let's focus on that middle triangle there where I have the x and the y. So let's just focus on, let me change this here. Let's highlight that. All right, so let's just kind of think about this triangle right in here. All right, so here's the triangle, kind of representative triangle here, that we're trying to find the one that has the biggest area. So when we think about the base, well, the base in this case is really this entire length from here to here. So that really represents our base. And then of course the height here, well, the height's pretty straightforward, right? So this is your height right there. So that's going to be your height. Okay, now, so I don't know if you can see that. So this is the height. All right, now as we look at then what does the x and the y mean? Well, good news is the height, this is really the definition of what the y variable is, going from here up to here. That is your definition for y. So that height is equal to y. However, the x distance is not the base because x would really just be the length from here over to where that x coordinate is. So from here to here, this is what x is. So that's going to tell us then that the full base, so from, here all the way over, is going to have to be twice that. So the base is going to be 2x. So there's our height was the y, and then the base is the 2x. All right, so let's bring this back. Oops, did not mean for that to be on there. And so we have 1/2. Our base is the 2x, and the height here is the y. All right, well, this is like it often is in terms of more than one variable. And so we need to get this in terms of just x or y, but in this case, what we want to also use is the fact then that this is a point on this parabola. So what we know is that the y coordinate has to equal 16 minus the square of the x coordinate. So that has to be the case if this point lies on the parabola. So here's what we know. We know that this y is going to equal 16 minus x squared. So the y is equal to 16 minus x squared. So we now have area as a function of x, and it's simply x times 16 minus x squared. All right, so pretty easy function actually to work with once we got it set up. It's just 16x minus x cubed. So taking our derivative, we're going to have 16 minus 3x squared. And then, of course, looking for where our derivative is equal to 0, because there isn't anything for where the derivative doesn't exist. So setting our 16 minus 3x squared equals 0, adding your 3x squared to the other side there, and then just dividing both sides by 3. You're going to have that your x squared is the 16/3. And then always remember, when you take your square root to get rid of the square, you have to know to introduce your plus or minus square root. And so we have x equals plus or minus square root of 16 is 4 over the square root of 3, or if you prefer, 4 root 3 over 3 in a rationalized form. And so, you could think of the positive one really being the one we're going to talk about. The negative one would be kind of the vertex, I guess, over in quadrant 2, if you were going to think about it. But of course, we haven't verified anything yet. So we need to verify, that's always the next step, that the x equals 4 over square root of 3 is actually giving us a max. And so let's do this with, I like second derivative tests, especially in cases where it's pretty quick and easy to take that second derivative, and it's really easy here. So the second derivative, the second derivative is just minus 6x, and then second derivative test just says sub that critical point into your second derivative, and you don't really care about the value, you just care about its sign. And so we are negative in our second derivative. That tells us we are concave down, and we are concave down in an interval that contains our critical point here of horizontal tangency at 4 over the square root of 3. So we are at a max. So we are at a max. All right, so this question, let's see what the actual question is. Find the largest area. So not the x or the y coordinate, but what is that area is the final question. So we can just sub it back into our a of x function here. Okay, so a of the 4 over square root of 3. would be this 4 over square root of 3 times 16 minus the 4 over square root of 3, quantity squared. And so we would have 16 minus 16 thirds if we square the numerator and the denominator there. And so, let's see here. So 32, no, hang on. So our 16 minus our 16 thirds. So that's going to give us, 32 thirds. I started to say that and then it didn't sound right to me. So 4 over square root of 3 times the 32 thirds here. And so that's really going to be what our area is. So we're going to end up with 128 over 3 square root of 3. And let's see, this is an area, so I guess we'll just say that is in square units. So this would be the actual max area. All right, so that's the last one in our optimization section.